Hello, this is Brian Albright. Welcome to the Digital Engineering 24/7 podcast. I'm here today with Phil Kinnane, Vice President of Sales at COMSOL, to discuss topics around simulation and democratization. Welcome to the show, Phil.
Thank you very much. I'm very happy to be here.
Great. Well, thanks for joining us. At Digital Engineering, we've spent a lot of time writing about this idea of simulation-driven design. At COMSOL, how do you see that concept playing out within your own customer base?
So traditionally, we've seen, and this is what I believe that most people understand with respect to simulation. Simulation-driven design is sort of a process where initially in the workflow of maybe designing a new process or a new device that you're going to be manufacturing. You want to understand the phenomenon itself and the different factors that affect it. You also want to try a number of hypotheses and run it through different, suite of parameters and so forth that would simulate the conditions and so forth that maybe this design will be subject to once it's in operation. And because of that, you can avoid having to build a number of prototypes or do a number of tests or experiments and so forth to try and find your way to a final optimized solution to your process or to the design of your device. Now, we, though, at COMSOL in the last few years have been looking at this in a slightly different way. Simulation is still very important. It's still, in the workflow itself, it still exists towards the beginning of the product life cycle, but it's not necessarily having to be done by the expert. It can also be done by the person who has possibly designed such devices, similar ones, has been working with the manufacturer of similar devices and their designs over many, many years, or maybe they've been running processes that are rather similar. And so by giving them the power of being able to do the simulation themselves, rather than having to go to some expert to do it, they can actually influence the initiation and the optimization of this design at a much with far greater accuracy and far quicker, so that gets their process or it gets their device and its manufacturer to market a lot quicker.
Mm-hmm. What sorts of things are driving this increased use of simulation or the increased interest in using simulation throughout the organization?
Well, there's a number of different things. I usually put it down to four factors. One of them is understanding. So it's no use sort of just putting stuff together based on experience that, this material or that material is something that we've always used. You should actually have a much better understanding in case there are potentially other materials that could be used or there are potentially other ways in which you can come to a solution to whatever it is that you're trying to achieve with respect to that design. From there, then, of course, there's the testing of different hypotheses. So you need to sort of consider the situations of which say it's a device that you're manufacturing. You have to consider the different sort of parameters and environments and so forth that this device is going to be subjected to. And so by being able to have a very good idea of how it's going to react in normal circumstances, but also in very abnormal circumstances, if you're trying to take into consideration catastrophic failure or the like, then being able to test that through a number of different simulations is a far greater and more efficient way to do it than actually having to try and produce these physical environments in some type of testing environment itself. And so cost, of course, and that is cost in that you don't need to produce these different testing environments, but also when you're actually come towards a final solution, a final design, you may want to shave off a bit of material here, or you may want to use a little bit less of energy there with respect to heating or some electricity that you're going to be putting into your process. And so you can save quite a lot of money by optimizing the design. And then finally, a factor that hasn't really been considered usually, or isn't often considered by the general populace, is that simulation is very important for quality analysis. So even after the process has been put into operation or after the device is being manufactured, you need to be able to test what the actual reality is to what was theoretically designed from the beginning. And if there are anomalies and differences, you need to really account for them so that you can ensure that whatever it is that you're running or whatever it is that you're building is exactly as you say it is.
We also write a lot about the idea of democratization of simulation, and you touched a little bit on this earlier. What does that mean for COMSOL? This notion of democratization.
The democratization isn't so much that we're opening up the sphere of simulation to a much larger number of people that can do it. In other words, it does involve that we're building a tool that can be used as a platform by simulation experts to themselves to create applications or even mini software, if you like, that can be used by non-specialists or non-simulation specialists in their field to simulate exactly the application or the process that they're working with. That's a traditional way of looking at democratization. What we see, though, with democratization is the communication associated with this. Because when I talk about specialists and I talk about smart people, people usually think of the modeling specialist, the person who knows the physics, the person who is very good at coding or once upon a time or is very good at the software that they're using to perform this simulation. But you need to remember that the person that they are subsequently producing the simulation for is often a very, very smart person and a very experienced person with whatever it is that they're working on. So if they are running a chemical plant, for example, they may have been running that chemical plant for 20 years and they know every valve and every pump and every pipe and every reactor or distillation column or whatever. And so they understand the actual intricacies of that plant a lot more than the specialist does. So when they themselves are able to play around with simulations rather than just having to be fed data from a simulation, if they themselves can play around with the simulation and put it through some different scenarios which may not have been thought of by the modeling specialist, then they can, of course, come back to the modeling specialist with feedback and actually learn the modeling specialist himself stuff about the thing that he's modeling for simulations, so that in the future he can do a much better job at creating those initial models. So it is that back and forth which we see as being democratization. It's not only that we're opening up a whole new power to a much greater audience of engineers and scientists, but it's also that we're allowing everyone from the modeling specialist to the operator to the engineer standing on the manufacturing floor the ability to communicate a lot better with each other and collaborate a lot better with each other.
What do you see then as some of the key challenges to enabling that type of usage of simulation?
Well, they're on two levels. The first is fairly technical. So how do you actually get the software out to people who are not who actually don't really consider themselves to be modeling specialists? Um, and on the technical level, that requires being able to send them these files, these applications, these mini software, if you like, in an effective way, so that if they're part of an organization, so that the organization still has full control over those mini software, those applications, in other words, so that they are used correctly. And so there's a bit of a hurdle there with respect to how you can actually make it available to a much larger number of engineers and scientists throughout an organization. But it's not particularly difficult because companies and organizations have been doing this with CAD software and with CAD models for quite some time. Um, but the bigger hurdle we find is that to actually convince either one, the physics or the modeling specialist, that it is actually possible for that these engineers that they've always been providing the models and the data from models to are first of all very smart people who themselves would in all reality be able to understand a simulation and play around with the simulation if it was simplified, so that they themselves don't actually need to know all of the underlying factors of simulating, but can understand the data that they put in and the data that they get out of it. So to get past that sort of hurdle, the modeling specialists will provide these other engineers and so forth with an app or a specified software that's very particular to an application or a design that design engineer is working with, and at the same time to have the engineer who's going to be expected to be doing these simplified but still rather sophisticated simulations, that they can do that. Having worked with physical stuff, or having worked in a chemical lab, or having worked with computer programs that are far simpler than a software like COMSOL's is, that they actually can work with something as sophisticated as COMSOL, and that they actually can play around with a number of different parameters, and find that by doing that they're either affirming what they always knew through experience, or by learning something new by actually putting their process or their design through some virtual tests.
Well, as a technology provider, then how else can COMSOL help these types of customers better utilize simulation?
By making it easy to use, which is usually the case with most software. But we have up until now made the COMSOL multiphysics software very easy to use. In other words, it's very intuitive, and it's also very flexible for the modeling specialist to be able to model any type of physics and couple that to any other type of physics. And whether you're doing that through ready-made interfaces that are applicable to a certain type of physics, that's one way of doing it, but also that flexibility through allowing these specialists to be able to type in their own equations, for example, and consider situations which aren't very usual or common, or some type of weird material that has its own special way of reacting to the conditions around it, can only possibly be described by experimental data, or be described by a fairly complex algebraic equation. So it should be very easy for that to be included into the software. That's coming from the modeling specialists side of things. But then, and of course, as I've been saying with these simulation applications that are used by design engineers or process engineers, that software should be very easy to use. So it should only have the inputs that are applicable to that person, that are understood by that engineer, available to them, and it should only have the outputs that are useful to them available to them. All of the underlying features of a model should be hidden, so that they don't have to worry about it or think about it, and can just run their simulations relatively easily, is also important. but in between is how do you get from the sophisticated model to the simplified app, and there we all have also designed a building tool, if you like, of these apps that includes a lot of drag and drop capability, includes the fact that you can record a lot of the steps in building a model, and then have that sort of be the underlying platform to an application. So it's all in the background, but it's expressed as a simple edit field or a simple drop down menu. So it's by making all of the different steps from going from the sophisticated model to the easy to use app, but doing it in a way that where you're not thinking so much about the software itself, but you're thinking about the application that you're trying to model.
All right. Well, I think that's it, Phil. Thank you very much for joining us today.
That was a pleasure, and I really enjoyed it.
Great. Thank you very much.